Okay, so in this movie clip, let's think about the non-ideal factors or the deviations from the ideal current voltage characteristic. Current versus voltage. So in the PN diode. 3A. Okay, so ideal diode uh, current voltage characteristic is this. Okay, and the diode equation is I is equal to I naught times exponential VA over thermal voltage KT over Q minus 1. But in rear diode, once you have any chance to measure the diode's IV characteristic, you're gonna see this plot. Slightly higher current can be measured at small forward bias. Okay, and it's going to be well matched to the ideal diode IV characteristic. And at some point, the data can be measured along a certain straight line. It looks like a register. So the diode can become register where very high forward bias. Okay, but most likely this regime can be used and uh, used in integrated circuit. All right, what about the reason under forward bias? Once you have a chance to measure the IV characteristic of a junction diode, you're gonna see that the monotonically increasing data point under reverse bias. As we have learned, the diode can flow very saturated current under reverse bias, but in real, the monotonically increasing data current flow can be detected and measured. Why is that? Think about this. And as we have learned at some point, the ideal diode can never go through the breakdown, but the practical diode would go through the breakdown mechanism like that. So at breakdown voltage, the exponentially increasing current can be uh, obtained in junction diode. So let me separate those four different deviations. Number one is, breakdown, but we have learned it. Zener breakdown mechanism and avalanche breakdown mechanism. Second one can be found here. In the ideal diode, the saturated current should be flown. However, certain additional current can be found. What is this? Let's think about that later. And in small forward bias, some another additional current can be flown. What is this? Why some more current can be flown than we have expected from based on ideal diode analysis? And very high forward bias, how come the diode can become resistive? This is a current versus voltage plot, and this slope indicates 1 over R. So this slope is kind of, straight line, so diode becomes resistor. Why is that? How come the diode can lose its own function under very high forward bias? What is the main physical reason? Well, actually, the answers for those three interesting mechanism. Well, the first one is definitely has been well answered with breakdown mechanism. So number two, number three, and here number four. What is the main mechanism? So the number two comes from the generation current. Number three comes from the recombination current. Number 4 comes from series resistance and or high level injection. So we are gonna learn those are three factors, three deviations from the ideal IV characteristic. So let's move on to the next movie clip. Next slide. Well, this is just only for your information, just to take a look at it and that's it. You don't need to spend your invaluable time to understand this. This is very advanced material, so just skip it if you want. All right, herein the NS band diagram. Let me change my color of pen. So here the NS band diagram for PN junction diode has been given. So this line indicates a Fermi energy level for P side, and this indicates a Fermi energy level on the N side. And as we have learned, this direction indicates voltage increasing, and that is voltage decreasing, so that the P side has been applied to a lower bias. In other words, under reverse bias now. Okay, so now I'm talking about this regime idea and rear, this part. So for a certain reverse bias, how come the additional current can be flown? In ideal diode analysis, the minority carrier, this electron, can be dived into the depletion region, and the minority carrier in the N side can be diffused into the depletion layer. So whatever the reverse bias is, whatever the energy barrier height is, the total amount of electron injection and total amount of hole injection on each side would be set, wouldn't be modified, wouldn't be varied because of this energy barrier height. Because this electron flow can be obtained from thermally generated electron hole pairs in the range of x of minus xp and x of minus xp minus ln. And in the N side, what is the physical origin for these holes? Yes, the thermally generated EHP in the regime of x of xn to x of xn plus LP. So within one diffusion length, thermally generated electron hole pairs are available, and most likely half of them can be injected into the depletion layer. But this mechanism is nothing to do with energy barrier height. In other words, this injection mechanism is nothing to do with Fermi energy level difference. Like again, this mechanism, this injection mechanism, is nothing to do with reverse bias magnitude. That's the main reason why we got the saturated current level under reverse bias in ideal diode. However, in real diode, some additional current can be detected. What is the physical origin for that? The answer can be found within the depletion layer. Within the depletion layer, the electron hole pairs can be dynamically formed. Once these electron hole pairs are happened, because of the built-in electric field, the electron can be swept into the N side, and hole can be swept or drifted toward the P side. And then this electron would move like that, and this hole would moves upward like a water bubble. Then think about the hole current and electron current. Hole is now moving toward the P side, so IP, hole current, can be formed from N to P. And now electron is moved from P to N, so that electron current can be formed from N to P. So by summing up I sub N and I sub P, IN plus IP, both are negative direction. Again, in PN diode, the positive current is defined as from the current value from P to N. But now, because of this electron hole pair happened in depletion layer, the IN plus IP becomes negative current value. I mean, the both IN, IP are flowing from N to P. So, go back to the IV characteristic in the reverse bias regime. The ideal diode analysis said that we have only taken into account this event and that event, but we didn't take into account this thermally generated EHP within the within the depletion layer. So this electron hole pair, thermally generated electron hole pairs in the depletion region would contribute to the current flow under reverse bias. So this amount, this current difference can be obtained, can be explainable from the thermally generated EHP in the depletion layer. Then the next question is, how come the additional current becomes more and more as reverse bias becomes more and more? This can be simply answered with your own knowledge. As reverse bias becomes intensified, it becomes more and more, the depletion layer width becomes wider and wider. And think about the total number of electron hole pairs thermally generated in the depletion layer. As reverse bias increases, I mean the magnitude of reverse bias increases, the depletion layer width becomes wider, so that total number of thermally generated electron hole pairs can become high. They can become more. So IN and IP, the current value from N to P becomes more. That's the reason why at a more reverse bias, more additional INIP can be obtained. Okay, but you may ask this kind of question: how come we didn't take into account? How come we didn't consider this impact, this effect, these events in ideal diode analysis? Go back to the assumption for ideal diode analysis. Again, please go back to the assumptions that we have used in ideal diode analysis, that there is a single line saying that we're going to ignore generation and recombination events in the depletion region. But in practical diode, the thermal generation, thermal recombination in the depletion region should be happened and should be taken into account in describing the practically or measured current versus voltage characteristic. Okay, all right. I guess that's all for today's movie clip. And next week, I'm going to explain some more. Yeah, this part number 3 and number 4 in the next movie clip, maybe next week. Okay, so thanks for your attention and see you in the next movie clip. Bye bye.